Okay, this is for minimizing and maximizing using linear programming. And I'm not going to do all your homework for you, obviously, but let's do problem number, 5 from your homework. Okay, the first thing I'm going to do is I'm going to list what your restrictions were. This we can read it a little bit better. Alright, here we go. This is problem number 5. Problem number 5, we have x plus y is greater than or equal to 8. Y is greater than or equal to 5. And x is greater than or equal to 0. And we're going to use these to generate what we call the feasible region for the answers. And we're trying to minimize the objective function 3x plus 2y. So the first thing I'm going to do is make sure I get these things into what I would call graphable form, but it's slope-intercept. Okay, so there is the first equation, or inequality. I've taken the x to the other side. My y-intercept is 8. 1, 2, 3, 4, 5, 6, 7, 8 right up here. And it goes down 1 over 1. And I'm going to make a few more of those points so I can draw that line real well. It looks just like that. And let's put that line in dark green here. So it looks like that pretty much. Looks pretty decent. Let's try one more shot at that. That one looks even better. There we go. And we are told to be greater than that, so we got to shade above this thing. This line continues on this way. And so here comes the shading. And then our other equation, y is greater than or equal to 5. Here is 5 right there. I apologize for the noise. And so y is greater than 5 is right there. And again, we have to shade that. So let's see if we can find a different color to shade in. Let's see here. There we go. That should be pretty light. And we want to be greater than that. So we can start to see that yellow and pink overlapping. And then our last line, x is greater than or equal to 0. So that's a vertical line at x is 0 going right up through there. And it looks just like that. And we want to be greater than that one, so let's pick another color here. There we go, nice blue shaded region. And so greater than this one is everything over here. And so we can see our feasible region, the region that has answers, is everything kind of here. Okay. And we want to minimize this function. Okay. And what's it saying? What that's saying is we can plug in with these 3 conditions. Any of these points I just drew those lines on in that hatch sort of region, I can pick any point in there, and those would be valid points. They'd fit condition 1, 2, and 3. But they won't minimize the function we want minimized. Okay? And we said minimums and maximums, those are located at vertexes of your feasible area. Well, our vertexes are right there and right there. So we've got 2 points. This first point looks like it's at 1, 2, 3, 5. And then this second point up here looks like it's at 0, 5, 6, 7, 8, 0, 8. And so one of those is going to minimize the function and meet all of those criteria that we have. And so we just find out what P is if we plug in 3, 5. At 3, 5, we get 9 plus 10. P is equal to 19. At the location 0, 8, plug in 0, we get 0, we plug in 8, and we get 16. We get 16, and so clearly our minimum for this function occurs at the ordered pair 0, 8, and it has a value of 16. And that's all.